Somewhere in our galaxy there's a neutron star that erupts without warning a cosmic heartbeat that suddenly explodes in bursts of energy. This is the bursting pulsar, one of the strangest objects ever observed. Tonight we'll explore why it behaves so wildly and what these sudden eruptions reveal about the extreme universe. If you enjoy discoveries like this, please like, subscribe and share, and tell us in the comments. What do you think triggers these unpredictable bursts? Thank you for watching. Now let's begin. Far out in the galaxy, the bursting pulsar sits as one small point inside the broad disk of the Milky Way, a thin, flattened structure of stars, gas and dark space that wraps around the galactic center. The disk stretches in all directions as a hazy river of starlight. When seen from Earth, but from a vantage above the plane, it would appear as a wide, dimly glowing band with brighter spiral arms curling slowly around a crowded core. Within this expanse, the neutron star occupies a modest orbit circling the center of the Milky Way, along with billions of other stars, each one following its own long, slow path through the galactic potential. The region around the bursting pulsar is not unique at first glance. The star resides in one of the spiral arms where dust-laden star-forming regions and older stellar populations coexist in a layered structure. The local patch of the galaxy contains ordinary stars like the Sun, dim red dwarfs and aged remnants that no longer shine brightly. Between them lies the interstellar medium, a diffuse mixture of gas and dust that fills the space between stars and shapes the passage of light. Radiation from the neutron star, including its sudden high-energy bursts, must cross this medium before it ever reaches Earth, and the properties of this environment leave subtle fingerprints on what telescopes detect. In the wide view, the bursting pulsar is simply a dot, but this dot flickers across time, and that flicker is what draws astronomers to study it in detail. The Milky Way itself provides the stage. Its spiral arms extend over many tens of thousands of light years, and in each arm dense clouds of cold gas collapse to form new stars, while older stars drift away along orbits that slowly change. The bursting pulsar moves through this scene as a compact, massive remnant of a long vanished star, yet nothing in the galactic setting marks it as unusual until its radiation is measured. From Earth, the line of sight toward the neutron star cuts through layers of galactic structure. In some directions, the path passes through crowded star fields near the inner regions of the Milky Way, where dust is thick and visible light is absorbed or scattered. In other directions, the view crosses clearer lanes where interstellar gas is more rarefied, allowing high-energy radiation to pass with less interference. The particular location of the bursting pulsar sets how much dust and gas lie in front of it, and this affects how bright the bursts appear at different wavelengths. X-ray and gamma-ray photons travel with little deflection, but lower-energy light can be dimmed or reddened, and radio waves can be dispersed, arriving at slightly different times depending on their frequency. Over large distances, small effects add up, and the galactic setting becomes a filter that reshapes the signal. Astronomers infer the distance to the bursting pulsar and the amount of material along the line of sight by measuring these changes in the observed radiation. When high-energy bursts occur, their light carries information not only about the neutron star itself, but also about the interstellar space between. The galaxy is not uniform. Patches of denser gas, known as molecular clouds, sit alongside more diffuse atomic gas, and hotter ionized regions, forming a complex clumpy structure that rotates slowly around the galactic center. The bursting pulsar orbits within this structure, its path determined by the combined gravity of stars, gas and dark matter. Over millions of years, its position within the spiral arm will drift, but on shorter timescales, it can be treated as fixed against the distant background. This stability allows long-term monitoring, as the same region of sky can be observed repeatedly by space-based and ground-based observatories. In the broad context of the Milky Way, the neutron star is only one of many compact objects. White dwarfs, other neutron stars, and black holes all share the galactic disk, each one a relic of past stellar evolution. Many of them are quiet, emitting only faint radiation, while a smaller fraction interact with companions or surroundings in a way that produces detectable signals. The bursting pulsar belongs to this active subset. When it erupts, its bursts briefly stand out above the diffuse glow of the galaxy at high energies, adding sharp, short spikes to the background emission. Yet these events unfold against a vast and relatively steady environment. The galactic plane emits a smooth band of light from countless unresolved stars and from gas excited by starlight and supernova shocks. Far above and below the plane, the stellar density drops, and the halo of the Milky Way takes over a region of older stars and dark matter that extends much further than the visible disk. The bursting pulsar remains tied to the disk embedded within one of its arms, moving on an orbit that keeps it near the plane for most of its journey. This position means that when Earth-based observers look toward it, they also see many foreground and background stars crowded into the same line of sight. Careful analysis is needed to separate the burst from other sources. Over time, surveys of the galactic plane build up maps of X-ray and gamma-ray emission, revealing both steady and transient sources. The bursting pulsar shows up in these maps as a recurrent transient, a source that remains at a low level most of the time, but occasionally brightens sharply when bursts occur. Even before details of the neutron star are considered, the fact that the source is located in the dense environment of the Milky Way disk suggests a history linked to massive star formation and violent stellar death, since neutron stars arise from supernova explosions of massive stars. The galactic setting therefore provides context to the system. It tells astronomers that this is a product of past star-forming activity in a spiral arm, that it lives among other remnants and evolved stars, and that its radiation must cross a structured, sometimes obscuring medium before reaching detectors. All of this shapes what can be observed and what remains hidden. The wide view stretching from the bright band of the Milky Way across the sky to the quieter regions of the outer disk and halo anchors the bursting pulsar within a living galaxy where stars are born, evolve and die over timescales far longer than the fleeting bursts that draw attention to this single neutron star. Radiation from the bursting pulsar leaves the vicinity of the neutron star and begins a long journey through the inner regions of the Milky Way, crossing a landscape of gas, dust and stars before it ever reaches Earth. The path that each photon follows is set by the geometry of the galaxy and the position of the source within the galactic disk. In directions that pass near the crowded central regions, the line of sight cuts through thick lanes of dust and dense gas clouds, while in other directions it moves through clearer, more diffuse stretches of interstellar space. The bursting pulsar lies at a particular galactic longitude and latitude fixed by its orbit around the galactic center, and that position decides which parts of the inner galaxy its radiation must traverse. Along this path, spiral arms of the Milky Way stack up in depth. Each arm contains stars, molecular clouds, and diffuse gas that together form a layered screen. Dark dust lanes, visible in optical images as irregular streaks that block starlight, are composed of tiny solid particles mixed with gas. These particles are efficient at absorbing and scattering visible light and ultraviolet light, while high-energy photons pass more easily. As the bursts from the neutron star travel outward, lower energy components of the emission are stripped away or dimmed by these dusty regions, while the most energetic X-ray and gamma-ray photons suffer fewer interactions and are more likely to reach distant observers. The line of sight therefore acts as a filter, changing the relative strength of the signal at different wavelengths. Observers studying the bursting pulsar see a version of the emission that has already been shaped by this interstellar filtering. Gas along the path absorbs some of the X-ray photons, especially those with lower energies. When astronomers measure how the brightness of the source changes with photon energy, they can infer how much gas lies between Earth and the neutron star. This total amount of gas, sometimes described as a column, along the line of sight provides a handle on distance and on the conditions in the inner galaxy along that direction. In some cases, dust grains near the source or along the path can scatter X-rays slightly, producing a faint halo around the point source when imaged with sensitive telescopes. For a bursting system, this halo can respond to changes in brightness with a delay because scattered photons travel a slightly longer route. These effects are subtle, but they show how the structure of the inner galaxy leaves its signature on the signal. At radio wavelengths, the line of sight plays a different role. Free electrons in the interstellar medium spread throughout the inner galactic disk cause radio pulses to disperse. Higher frequency waves travel more quickly through this plasma than lower frequency waves, so a sharp pulse emitted by the neutron star arrives at different times when observed at different radio frequencies. By measuring this delay, astronomers can estimate the number of electrons along the path and again recover information about the inner galactic environment. For a bursting pulsar, if radio pulses accompany the high-energy activity, their dispersion provides a second independent probe of the path the radiation has taken. The line of sight is not static. Gas clouds move in response to galactic rotation, and local motions and small-scale fluctuations in electron density can act like lenses that focus or defocus radio waves. This can cause the apparent brightness of the source to vary slowly even when the intrinsic emission remains steady. Astronomers call this scintillation, an effect similar in spirit to the twinkling of stars as seen through Earth's atmosphere, but taking place instead in the interstellar medium of the inner galaxy. Against this gently changing background, the sudden bursts stand out as rapid, sharp increases in high-energy flux, but disentangling intrinsic changes from line-of-sight effect requires careful analysis. The path also crosses regions of hot ionized gas near older supernova remnants and star-forming complexes, as well as cooler, more neutral areas where hydrogen atoms absorb certain wavelengths. When radiation from the bursting pulsar encounters these regions, specific patterns of absorption appear in its spectrum. By comparing observations over many bursts and over long periods of time, astronomers build up a picture of the layered structure of gas and dust between the neutron star and Earth. This picture is not perfectly detailed, and uncertainties remain about small-scale clumping and the exact distribution of material, but the broad features are well constrained enough to place the bursting pulsar within the inner structure of the Milky Way with reasonable confidence. Closer to Earth, the path enters the local interstellar environment around the Sun, where gas density is relatively low compared with some inner galactic regions. Here, the radiation passes through a bubble of hot, tenuous plasma thought to have been carved by ancient supernova explosions. The effect of this local region on high-energy bursts is modest, but it forms the final segment of the interstellar journey. After crossing this space, the photons reach the vicinity of Earth and encounter the planet's magnetosphere and atmosphere. The atmosphere blocks most X-rays and gamma rays, so the final detection of the bursts relies on space-based observatories orbiting above the absorbing air. In this way, the line of sight can be thought of as a sequence of distinct environments: dense inner disk regions, spiral arm clouds, more diffuse outer gas, local hot plasma near the Sun, and finally the near-Earth surroundings. Each environment leaves its own imprint. The presence of dust shapes the colour and intensity of any lower energy light from the neutron star. Gas sets how strongly X-rays are absorbed at different energies. Electrons control the dispersion and scintillation of radio pulses. The net result is that the observed behaviour of the bursting pulsar is always a combination of what the neutron star emits and what the inner galaxy allows through. Some aspects of this path are well understood, supported by decades of observations of many sources along similar directions. Others remain less certain, especially the smallest structures that cannot be fully resolved. For the bursting pulsar, these uncertainties mean that some properties, such as its exact distance, or the fine details of how its bursts are modified in transit, carry error ranges. Even so, the line of sight through the inner Milky Way is mapped well enough to serve as a stable framework. Within this framework, each new burst adds another brief sharp signal that has threaded its way through the complex structure of the galaxy, allowing astronomers to refine their understanding of both the source and the medium between stars. Around the bursting pulsar, the local stellar neighbourhood forms a quiet backdrop of light motion and long timescales. Seen from a distance, this patch of the Milky Way is a modest concentration of stars within the broader spiral arm, neither an especially dense cluster nor an empty void. Ordinary stars dominate the view. Many are cooler, smaller red dwarfs that shine faintly in visible light, but are numerous, filling the region with a soft, low, level glow. Others are stars roughly similar to the Sun, with temperatures and luminosities that place them near the middle of the main sequence, where hydrogen fusion in their cores proceeds steadily over billions of years. A smaller number of more evolved stars add variety to the landscape, red giants with swollen envelopes and cooler surfaces, and occasional blue or white subdwarfs that trace advanced stages of stellar evolution. Against this array of luminous objects, the neutron star itself is almost invisible at optical wavelengths, its compact surface emitting little visible light compared with its high energy output. The stellar neighbourhood is not static. Each star moves under the combined gravitational field of the galactic disk, following an orbit around the galactic centre, while also carrying its own peculiar motion relative to nearby stars. Over many millions of years, these motions gradually reshuffle the pattern of neighbours, but on human timescales the configuration appears essentially fixed. The bursting pulsar and its nearby stars share a common bulk motion as part of the same spiral arm population, drifting together around the Milky Way. Some of these stars may have formed in the same large-scale complex of gas clouds that once gave birth to the massive progenitor of the neutron star, while others were born elsewhere and have since passed through this region. Astronomers study the stellar population around systems like this to infer the age and origin of the environment. The mix of older, less massive stars, the relative absence of very young massive ones, and the kinematics of the group suggest a mature patch of the disk, rather than a newly formed star cluster. This is consistent with the presence of a neutron star, which requires a massive star to have lived, evolved, and exploded in the past. The neighbourhood also contains dark unseen components. Compact remnants such as white dwarfs and other neutron stars likely reside within a few tens of light years, though most remain undetected unless they accrete matter or emit beamed radiation. Stellar mass black holes may also be present, the end products of even more massive stars that collapsed without leaving a bright remnant. These objects contribute to the gravitational field but not to the visible light in the region. In this way, the local neighbourhood around the bursting pulsar represents a typical slice of the older stellar disk, where visible stars and compact remnants coexist within a shared volume of space. Interstellar gas in this immediate surroundings is relatively thin compared with the denser molecular clouds found in active star-forming regions. The gas is mostly warm and diffuse, with occasional patches of cooler, denser material that represent remnants of past clouds or the outskirts of current ones. This lower density environment means that the immediate vicinity of the neutron star is not dominated by the effects of ongoing star formation. Instead, it is shaped by past events, including the supernova that formed the neutron star and earlier generations of stellar winds and explosions that have stirred and heated the gas. The local density of stars influences how often close encounters occur over long timescales. In a dense globular cluster, frequent interactions between stars and binaries can strongly modify orbits and even exchange companions. In the more modest density typical of the galactic disk, such close interactions are rarer. The bursting pulsar and its companion star therefore likely evolved together over a long period without strong external perturbations, aside from the initial supernova that created the neutron star. The binary moves through the local stellar field, but neighbouring stars remain at distances where their gravitational influence is gentle and cumulative, rather than sudden and disruptive. Observationally, the stellar neighbourhood appears in images as a collection of point sources of different colours and magnitudes scattered across the field. The bursting pulsar itself often does not stand out in visible light, especially if it is distant or if dust obscuration is significant along the line of sight. Instead, its presence is revealed primarily in X-rays or gamma rays, where high-energy bursts and persistent emission can be localized with space-based instruments. Once the coordinates are known, astronomers can examine deeper optical and infrared images to search for the companion star and to characterize the surrounding stellar population. The colors and brightnesses of nearby stars trace the distribution of stellar masses and ages in this region. A dominance of lower mass older stars indicates that the area is part of an evolved disk population, while the presence of bright massive stars would signal more recent star formation. Around a typical bursting pulsar, the evidence points to an environment where the most massive stars that once existed have already ended their lives, leaving behind compact remnants and more modest companions. This is consistent with the requirement that the neutron star arises from a star that was originally significantly more massive than the Sun, and that has already passed through all its nuclear burning stages to reach collapse. Proper motion measurements, when available, allow astronomers to track how the bursting pulsar system moves against the background of more distant stars. These motions can be combined with radial velocity measurements to reconstruct the full three-dimensional velocity of the system within the galaxy. Sometimes neutron stars receive a kick during their birth in a supernova, imparting an additional velocity component that can carry them away from their original birthplaces. In the case of a bursting pulsar in a binary system, the fact that the system remains bound suggests that any kick was not strong enough to unbind the pair, but it may still have altered their orbit and drift relative to the surrounding stellar population. Over millions of years, this motion can move the system into a different part of the disk from where it formed. Even so, at any given moment, it is one member of a broad ensemble of stars sharing similar galactic orbits and long-term trajectories. The local stellar neighborhood also provides a reference frame for the radiation emitted by the bursting pulsar. High-energy bursts originate from a compact region near the neutron star, but when they reach Earth, they appear superposed on the light from neighboring stars. Instruments that observe high energies typically have limited angular resolution compared with optical telescopes, so careful analysis is needed to assign the burst to the correct position among many potential counterparts. By comparing high-energy positions with precise optical or infrared images, astronomers can isolate the correct star system and build a complete picture that includes both the compact object and its local environment. In this way, the stellar neighborhood is not just a backdrop but an essential context that helps interpret the observations. It reveals the kind of galactic environment the bursting pulsar inhabits, constrains the history of star formation in the region, and offers hints about how common similar systems might be. The presence of many other stars at various evolutionary stages underscores that the bursting pulsar is one outcome among many in the long cycle of stellar birth, evolution and death that unfolds in the disk of the Milky Way, even though attention is drawn to it by the sudden intense bursts that occasionally shine out from this otherwise quiet patch of sky. Long after the massive star that once occupied this region has ended its life, the space around the bursting pulsar still bears quiet traces of that event. The supernova that created the neutron star has already faded from any dramatic display, yet its consequences persist in the arrangement and composition of the nearby gas. A very long time ago, in human terms, the progenitor star reaches the end of its nuclear fuel and undergoes core collapse, sending a shock wave outward into the surrounding interstellar medium. Now what remains of that shock is an expanding shell of gas that has slowed and cooled as it sweeps up material from the environment. In some systems, this shell appears as a clearly defined supernova, remnant observable in radio X-ray or optical emission lines, with filaments and arcs tracing where the shock front compresses and heats gas. In others, the structure has become diffuse and hard to distinguish from the general background. For the bursting pulsar, the evidence for a surviving remnant may be subtle. Astronomers search for faint extended emission near the position of the neutron star, looking for patterns that suggest an expanding bubble of enriched gas. They examine radio maps for shells or partial arcs, and they study X-ray images for patches of hot plasma that might trace the decaying shock. Sometimes they find a clear match with the neutron star located near the center, or slightly offset consistent with the natal kick that has moved it away from the geometric center of the remnant. In other cases, no distinct structure is seen either, because the remnant is too old and faint, because the ambient medium is too irregular, or because the original explosion energy and environment produce a morphology that blends into surrounding clouds. Even when a visible shell is not obvious, the chemical imprint of the supernova remains. The progenitor star synthesizes heavy elements in its core and outer layers during its life and final collapse. When the explosion occurs, these elements are ejected into space, mixing with the ambient interstellar medium. In the vicinity of the bursting pulsar, gas may carry enhanced levels of elements such as oxygen, neon, or iron, relative to regions that have not recently experienced such an event. Detailed spectroscopic measurements of nearby gas, when possible, reveal emission lines whose strengths reflect these abundances. Over time, turbulent motions and large-scale galactic rotation stir this material, spreading enrichment over wider volumes. The local environment around the neutron star thus participates in the broader process by which supernovas seed the galaxy with heavy elements. The geometry of the remnant, whether sharply defined or diffuse, also influences how the neutron star moves through space. The explosion does not always expel matter symmetrically, and the newly formed neutron star can receive a velocity kick. This kick, combined with the pre-existing orbital motion of the progenitor star around the galactic center, gives the neutron star a trajectory that may not align exactly with the center of any surviving shell. As a result, in systems where the remnant is still visible, the compact object is often found offset from the geometric center. Astronomers use this offset together with estimates of the age of the remnant to infer how fast the neutron star travels and in which direction. In the case of a bursting pulsar in a binary, the situation is further shaped by the need for the binary to remain bound after the explosion. This requirement limits how strong the kick can be and still allow the companion star and neutron star to orbit each other. The fact that a close binary exists today suggests that the supernova has unfolded in a way that preserves the pair, even if it alters their orbit. The expanding shock wave from the supernova interacts with the surrounding medium, compressing some regions and rarefying others. As it moves outward, it heats gas to high temperatures, causing it to emit X-rays that gradually fade as the gas cools and mixes. It also drives waves that can trigger or inhibit future star formation in nearby clouds depending on the local conditions. In 3 dimensions, the remnant is not a perfect sphere. Density variations and magnetic fields shape its expansion, producing a complex pattern of filaments and cavities. Over long timescales, this structure becomes less distinct, but remnants that are still relatively young compared with galactic timescales retain enough contrast to be studied in detail. The bursting pulsar residing within or near this evolving volume is part of this ongoing interaction between expelled stellar material and the interstellar medium. Observations across different wavelengths provide complementary views of the supernova aftermath. In radio frequencies, synchrotron emission from relativistic electrons spiraling in magnetic fields outlines the structure of the remnant and reveals where shocks continue to accelerate particles. In optical bands, emission lines from ionized atoms trace regions where gas is dense enough and cool enough to radiate strongly. In X-rays, hot plasma produced by the original shock and by subsequent interactions glows, offering insights into temperatures and densities reached in the collision between ejector and ambient gas. By fitting models to these observations, astronomers estimate parameters such as the explosion energy, the density of the surrounding medium, and the age of the remnant. For some bursting pulsars, these parameters remain uncertain, because the remnant is faint or confused with unrelated structures along the line of sight. In such cases, indirect constraints such as the spin age of the neutron star or the properties of its magnetic field provide complementary information on how long it has been since the supernova. The immediate neighborhood of the neutron star may also bear evidence of past interaction with the expanding shell. If the system moves through the interior of the remnant, it encounters gas with different density and temperature compared with the undisturbed interstellar medium. This can affect the structure of any bow shock that forms as the neutron star plows through gas, and it can influence how material from the companion star later spreads into the environment. While the detailed shapes of these features are complex and sometimes poorly constrained, the broad picture that emerges is consistent across many systems. A massive star ends its life, ejects material and energy, leaves behind a compact remnant and reshapes the local interstellar medium in ways that persist for hundreds of thousands of years or longer. In the environment around the bursting pulsar, the supernova is no longer an active explosion, but its echoes remain imprinted in temperature gradients, chemical abundances, and subtle density structures. These remnants of violent change now form part of a calm backdrop against which the neutron star evolves, and in this particular system accretes matter and produces bursts. The contrast between the quiet present state of the remnant and the brief intense activity near the neutron star underscores the layered nature of time in astrophysical settings. On the longest scales, the supernova remnant slowly dissipates into the galactic medium, its gas blending with the surroundings. On shorter scales, the neutron star rotates, accretes, and bursts, drawing attention back to the compact object that the explosion has left behind. Regardless of whether the remnant is clearly visible or only inferred, it remains an essential part of the story of the bursting pulsar, providing both the origin of the neutron star and the structure of the medium through which its later emission must travel. At the heart of the system, the bursting pulsar does not move alone. It shares its region of space with a companion star bound together by gravity in a continuous orbit that traces an elongated yet regular path through the surrounding darkness. The companion is a normal star by galactic standards, yet its presence is crucial for the behavior of the neutron star. Without a partner to supply fresh material, the compact object would slowly cool and fade, emitting only the residual energy stored from its birth. Instead, the companion provides a steady if sometimes variable flow of gas that eventually drives the bursts, and the geometry of their mutual orbit sets the stage for how this transfer unfolds. In many bursting systems, the companion has a mass comparable to, or somewhat less than that of the Sun, and it often appears as a main sequence or slightly evolved star with a surface temperature that gives it a yellow-orange or even cooler reddish hue. Its radius is much larger than that of the neutron star, extending out to fill a significant fraction of the space within their orbit. In visible light, it dominates the appearance of the binary, since the neutron star is too small and faint to contribute much at those wavelengths. From a distance, then, the system resembles an apparently ordinary star with the extreme compact object revealed only through its high energy emission. The two bodies move around a common center of mass, a point that lies closer to the more massive object. The neutron star, containing more mass than the companion, despite its small size, holds the dominant share of the gravitational pull, so the center of mass lies deep within its orbit, yet still displaced from the neutron star itself. Both objects circle this point, completing orbits on timescales that can range from less than an hour to many days, depending on the separation and masses involved. The orbit is often nearly circular, the result of tidal forces and mass transfer that act over long periods to round out any earlier elongation, though in some systems a modest eccentricity remains. As they revolve, the distance between neutron star and companion stays almost constant in a circular case setting a stable gravitational configuration. This orbital dance defines a special surface in space called the Roche lobe. For each star, a tear-shaped boundary within which material remains bound to that object. The Roche lobe of the companion is especially important. If the star expands or if the orbit shrinks so that the stellar surface approaches this boundary, gas near the outer layers can feel nearly equal gravitational pulls from both stars. Once the surface reaches or exceeds the Roche lobe, material can flow across the inner point between them, the so-called inner Lagrange point, and fall toward the neutron star. Even if the companion is slightly smaller than this critical size, strong stellar winds can still carry gas outward, or it may be captured by the compact object. The degree to which the companion fills its Roche lobe therefore controls how strongly it feeds the neutron star. The structure of the companion reflects its evolutionary stage. A main sequence star retains hydrogen fusion in its core, producing a steady luminosity. Its outer layers are relatively stable, and its size changes only slowly on timescales far longer than human lifetimes. An evolved companion, such as a subgiant or red giant, has exhausted core hydrogen, and has begun to expand, cooling its surface and increasing its radius. In such cases, the star can approach or exceed its Roche lobe more easily, leading to enhanced mass transfer. The bursting pulsar may inhabit either kind of system, but the rate and stability of accretion from the companion depends sensitively on these stellar properties. Astronomers infer details of the companion by studying its spectrum, its brightness, and its orbital motion. When light from the star is dispersed into a spectrum, absorption lines from various elements become visible. The pattern and strength of these lines reveal the star's temperature, surface gravity, and chemical composition. Periodic shifts in the wavelengths of these lines, caused by the Doppler effect as the companion moves toward and away from Earth, during its orbit, allow measurements of its radial velocity. By tracking these shifts over time and combining them with knowledge of the orbital period, researchers can estimate the mass function of the system, placing constraints on the masses of both the neutron star and its companion. In some favourable cases, eclipses occur when one object passes in front of the other, from the observer's viewpoint, causing a dip in brightness that can be measured with high precision. These eclipses, if present, provide further constraints on the orbital inclination and on the relative sizes of the bodies. Even when eclipses are absent, the orbital motion leaves imprints on the timing of pulses and bursts, as the neutron star moves closer to and farther from Earth in a regular pattern. By analysing these timing variations, astronomers can reconstruct the orbit with remarkable detail. Within the binary, tidal forces operate continuously. Each star raises tides on the other, distorting their shapes slightly from perfect spheres and dissipating energy in their interiors. Over long periods, these tidal interactions tend to synchronize the rotation of the companion with the orbit, leading to a state where the same side of the star always faces the neutron star, similar to how the Moon keeps one face toward Earth. They also tend to circularize the orbit. These processes may already be complete in a mature bursting system, leaving a nearly circular orbit and a companion whose rotation is locked to the orbital period. The side of the companion that faces the neutron star experiences a different radiation environment from the far side. High-energy photons from the neutron star, particularly during active phases, can heat this inner hemisphere, causing temperature contrasts across the stellar surface. This heating can produce subtle variations in the brightness of the companion, as seen from Earth over the course of an orbit, because different parts of the heated and unheated surfaces come into view. By modelling these variations, astronomers gain another independent probe of the binary geometry, including the inclination of the orbit and the degree of heating. The orbital separation measured in units of the companion's radius and the size of the Roche lobes sets the gravitational potential through which any escaping material must move. Gas leaving the companion does not fall straight inward. Instead, it retains the orbital angular momentum of the star and follows a curved path, forming streams, and under many conditions a disk around the neutron star. The details of this process belong to the accretion environment, but the initial conditions are dictated by the binary configuration described here. A tighter orbit with a nearly Roche lobe-filling companion encourages steady high-rate mass transfer, while a wider orbit with a smaller star may lead to weaker intermittent feeding controlled by stellar winds. The long-term evolution of the binary is governed by exchanges of mass and angular momentum between the two stars and their orbit. As the companion loses mass, its structure can change, adjusting its radius and internal profile. The orbit itself can widen or shrink depending on how mass is lost from or redistributed within the system. Magnetic braking, gravitational radiation, and mass loss through winds all contribute small but cumulative effects. The current state of the bursting pulsar system represents one moment in this ongoing evolution, a stage in which the orbital period separation and companion properties permit the specific pattern of accretion that leads to bursts. Yet, on the timescales relevant for human observation, these parameters remain essentially constant, providing a stable framework within which the bursts can be studied. From the standpoint of the broader stellar neighbourhood, the binary appears as a single, moving light source, tracing a gentle arc across the galaxy. Within that light source, however, the geometry of the orbit, the mass and temperature of the companion, and the precise shape of the Roche lobes define the gravitational landscape around the neutron star. This landscape governs how matter can flow, how energy is exchanged between the stars, and how the neutron star is supplied with the fuel that it later releases in sudden intense episodes of high-energy radiation. The companion star is therefore not just an incidental neighbour, but an active partner, its structure and orbit forming the immediate outer framework of the bursting pulsar system. Once the orbital configuration of the binary has brought the companion star close enough to its Roche-Lobe mass transfer, begins to shape the inner life of the system. Gas in the outer layers of the companion no longer finds itself securely bound solely to that star. Near the inner Lagrange point where the gravitational pulls of the neutron star and the companion nearly balance, and where the centrifugal effects of orbital motion also matter, a narrow passage opens. Through this region, material can slip away from the companion and start falling toward the neutron star. The process is quiet on human timescales, yet relentless. In the outer atmosphere of the companion, thermal motions and turbulence jostle atoms and ions. Where the star comes closest to filling its Roche-Lobe, a slight outward push, whether from internal pressure or small changes in the stellar radius, can carry gas across the critical surface that defines gravitational binding. Once beyond that contour, the matter feels a stronger net pull toward the neutron star and begins to move in that direction. Because it originates from a star already in motion around the common center of mass, the gas carries orbital angular momentum with it. As a result, the path it follows is not a straight line inward, but a curved stream that arcs around the neutron star. In a frame of reference co-rotating with the binary, this stream may appear as a nearly steady flow, leaving the companion through the inner point and threading a path through the inner space between the stars. The density, speed, and steadiness of this gas stream depend on how fully the companion fills its Roche-Lobe and on how its structure responds to losing mass. If the star just grazes the boundary, mass transfer can be relatively gentle and stable, with gas flowing at a rate that changes slowly as the orbit evolves. If the star overfills its Roche-Lobe more substantially, the transfer can be more vigorous, potentially leading to phases of enhanced accretion. In some systems, external factors such as magnetic activity or stellar pulsations add modest variability to the outflow. However, the broad picture remains that gravity and orbital motion together shape a stream that continuously feeds the region around the neutron star. In addition to Roche-Lobe overflow, stellar winds can contribute to, or even dominate mass transfer in some binaries. Many stars lose mass in the form of winds driven by thermal pressure radiation or magnetic processes. These winds carry gas out into the surrounding space in all directions. When a neutron star orbits within such a wind, its strong gravity focuses and captures a fraction of the outflow. The net result is a flow of gas toward the compact object that is less constrained in geometry than a narrow Roche-Lobe stream, but still guided by the gravitational field. For the bursting pulsar, the relative roles of Roche-Lobe overflow and wind accretion depend on the specific properties of the companion. Systems with more compact lower mass companions tend to favor Roche-Lobe overflow, while those with more massive luminous companions often rely more on winds. Regardless of the exact mechanism, the key outcome is that a continual supply of gas is delivered into the gravitational influence of the neutron star. As the stream moves inward, it experiences changing forces. The gas leaves the companion with a speed comparable to the orbital velocity at the inner point, then accelerates under the neutron star's gravity. However, its angular momentum prevents it from plunging directly onto the compact object. Instead, the trajectory curves, sometimes overshooting the neutron star and wrapping around it. Collisions within the stream and with any previously accreted gas cause shocks, heating the material and spreading it out. In many cases, this process leads naturally to the formation of an extended accretion structure. But even before that structure is fully established, the region near the neutron star is already filled with spiraling gas, whose motion encodes the balance between gravity, pressure, and rotation. The transfer of mass from the companion to the neutron star is accompanied by a transfer of angular momentum. As gas moves inward, its angular momentum must be redistributed. Some of it is carried into the innermost regions where it can influence the spin of the neutron star over long timescales, gradually spinning it up towards shorter rotation periods. Some is transported outward within the flow, allowing material at small radii to move inward, while gas at larger radii moves slightly outward. The details of this transport involve viscosity turbulence and magnetic fields, all of which are active within the accretion environment, though their exact roles and efficiencies remain areas of ongoing research. From an energetic perspective, mass transfer is the first step in converting gravitational potential energy into heat and radiation. Gas originally deep in the gravitational well of the companion star finds itself, after crossing the inner point, falling into a much deeper well around the neutron star. The difference in potential energy between its starting position and its final resting place near the compact object is substantial. As the gas sinks inward, this energy must go somewhere. Some of it appears as bulk kinetic energy in the motions of the stream. Some is converted into thermal energy through shocks, collisions, and viscous interactions, raising the temperature of the gas. Eventually, much of this energy is radiated away as electromagnetic emission, particularly in high-energy bands such as X-rays. However, at the stage of the gas stream itself, most of the radiation remains modest, with the brightest emission arising once the material has settled into the inner accretion regions. The flow of mass is not necessarily perfectly smooth. Small variations in the companion's radius magnetic activity cycles or structural changes can alter the rate at which gas crosses the Roche lobe. In wind-fed systems, changes in wind strength and structure introduce further variability. These fluctuations can propagate into the accretion flow, leading to changes in the brightness and spectral properties of the system over timescales that range from minutes to years. Observationally, such variability appears as changes in the persistent high-energy emission level, as well as in the properties of any pulses associated with the neutron star's rotation. For bursting pulsars, the overall accretion rate provided by the gas stream sets the background against which bursts occur. At higher accretion rates, the supply of fresh material onto the neutron star surface is more rapid, influencing how quickly conditions build up for instabilities that lead to bursts. At lower rates, the build-up is slower, yet the accretion rate itself can be influenced by feedback from the neutron star. Strong radiation from near the compact object can heat and ionize gas in the inner parts of the stream, altering its structure and possibly pushing some material away. Magnetic fields associated with the neutron star can also interact with the inner flow, shaping how gas is channeled inward. These couplings between the stream and the compact object add complexity to the mass transfer process, and while the general framework is understood, many details remain subjects of active theoretical and observational work. The geometry and steadiness of the gas stream also determine how observable certain features become. In some systems, optical and ultraviolet light produced where the stream first strikes an existing disk creates a localized bright spot which can be tracked as it moves with the orbit. In others, emission lines from gas in the stream reveal its velocity structure when studied with high-resolution spectroscopy. These signatures help astronomers map the flow of matter in 3 dimensions, confirming that gas indeed moves from the companion toward the neutron star along the predicted pathways. They also allow estimates of the mass transfer rate, independent of the high-energy luminosity, providing a cross-check on models that link accretion to observed X-ray output. Over long timescales, the balance between mass loss from the companion and mass gain by the neutron star slowly alters the system. The companion gradually loses mass, which can change its internal structure and radius. The neutron star gains mass and angular momentum, potentially affecting its spin and internal state. The orbit responds as well, adjusting to the new mass distribution and to any loss of matter from the system altogether in winds or jets. These slow changes proceed over millions to billions of years, far longer than the timescales of the bursts themselves, but they set the larger context in which short-term phenomena occur. At the present stage, the bursting pulsar exists in a configuration where mass transfer through a gas stream is active and sustained, delivering a steady supply of material into the deeper gravitational well of the neutron star. This stream, invisible to the eye, yet traced by its energetic consequences, is the bridge between the ordinary star and the compact object carrying gas from a relatively benign, stellar atmosphere into an environment where extreme gravity, magnetic fields and high-energy radiation govern its fate. As gas from the companion star continues to flow toward the neutron star, the region around the compact object develops a broad accretion environment in which matter settles into organized motion rather than plunging straight inward. The stream leaving the inner point between the stars arrives in the gravitational field of the neutron star, carrying angular momentum inherited from the orbit. This angular momentum prevents the gas from falling directly onto the compact object. Instead, the stream loops around, colliding with itself and with gas that has arrived earlier, and spreads out into a flattened, rotating structure that forms the outer parts of an accretion disk. In this outer disk, the distance from the neutron star is still large compared with the size of the compact object, but the gas is firmly bound to its gravity and moves on nearly circular paths. Each parcel of gas orbits the neutron star at a speed set by the balance between gravitational pull and centrifugal tendency. Closer orbits are faster, more distant orbits are slower, so the disk rotates differentially with inner rings of gas lapping outer rings over time. This difference in orbital speed is central to how the disk evolves. The gas in the outer accretion environment is not a perfectly smooth laminar flow. Small irregularities in density, temperature and velocity lead to turbulence and magnetic fields, thread the plasma tying together regions at slightly different radii. These conditions allow angular momentum to be transferred outward through the disk while mass moves inward. In theoretical models, this transport is often described in terms of an effective viscosity, a property that measures how efficiently momentum is redistributed between neighboring layers of fluid. The microscopic origin of this effective viscosity in astrophysical disks is not fully settled, but many lines of evidence point to magnetically driven turbulence as a key mechanism. Regardless of the detailed process, the outcome is that gas at smaller radii can lose angular momentum and drift slowly inward, while gas at larger radii gains angular momentum and drifts outward, allowing the disk to spread over time. In the outer parts of the disk around a neutron star, temperatures are high compared with ordinary stellar atmospheres, but low compared with the innermost regions. The gas is heated by friction and by the release of gravitational energy as it moves inward, but at large radii this heating is moderate. The material may be partially ionized with electrons and ions moving freely enough to respond to magnetic fields, yet dense enough that collisions are frequent. The disk here is geometrically thin, meaning its vertical thickness is small compared with its radius. The bulk of the mass lies in a narrow band around the orbital plane of the binary. Above and below this plane, the density drops off, merging into a more tenuous halo of gas that surrounds the disk and interacts with any outflows or winds that the system may produce. Radiation from the outer disk emerges mainly in optical and ultraviolet wavelengths, with some contribution in X-rays when temperatures are higher. The specific spectrum depends on the local temperature distribution, which in turn reflects how much energy is dissipated at each radius and how efficiently that energy is radiated away. In the outer environment, the surface of the disk can radiate approximately like a series of overlapping heated rings, each ring emitting radiation characteristic of its temperature. Astronomers can model this emission and compare it with observations to infer properties such as the disk's outer radius, its temperature profile, and the rate at which mass is flowing through it. The outer edge of the disk is constrained by the gravitational influence of the companion star and by tidal forces within the binary. If the disk tries to extend too far outward, tidal interactions with the companion can truncate it, stripping material from the outermost regions or forcing it into resonant orbits that become unstable. As a result, the disk tends to occupy a limited radial range with an outer boundary set by the balance between the neutron star's gravity and the perturbing effect of the companion. Within this region, spiral density waves can arise as the disk responds to tidal forcing. These waves are patterns of enhanced and reduced density that circle the disk, somewhat analogous to the spiral structure of a galaxy, though on a much smaller scale and with different underlying physics. They play a role in transporting angular momentum and can contribute to subtle variations in the disk's brightness over time. At the point where the incoming gas stream from the companion strikes the outer edge of the disk, a localized region of enhanced heating forms. The stream arrives with a specific trajectory and velocity, often intersecting the disk at an oblique angle. The collision between the stream and the rotating disk material creates shocks that convert kinetic energy into heat and radiation. This impact region, sometimes called a hotspot, can emit strongly in optical and ultraviolet bands and can rotate with the orbital period. When the system is observed over many orbits, the changing visibility of this hot region can produce a periodic modulation in brightness. By studying these modulations, astronomers gain further constraints on the geometry and orientation of the accretion environment. The overall structure of the outer accretion disk is shaped by a balance between gravity, centrifugal effects, pressure radiation, and magnetic forces. Gas pressure supports the disk against vertical collapse, maintaining its thickness. Gravity from the neutron star pulls material inward and toward the midplane. Centrifugal tendencies push material outward in the radial direction, preventing it from falling inward without first losing angular momentum. Radiation carries away energy, cooling the disk and allowing it to settle into a quasi-steady configuration where heating and cooling roughly balance over long timescales. Magnetic fields, both inherited from the companion's wind and generated within the disk itself, weave through the plasma, connecting different regions and enabling the transfer of angular momentum that drives accretion. The outer accretion environment is not purely axisymmetric in practice. Clumps, warps, and local variations can arise from changes in the mass transfer rate, from interactions with the binary orbit, or from internal instabilities. These features may precess or move slowly around the disk, altering the detailed pattern of brightness, as seen from different angles. In some cases, the disk can become slightly tilted relative to the orbital plane, leading to a warped structure that causes periodic changes in the observed light curve as different parts of the disk move into and out of view. Such behaviors are observed in a number of accreting neutron star systems and are interpreted through models that incorporate the complex interplay of radiation pressure, magnetic torques, and tidal forces. Despite these complexities, the outer accretion disk around the bursting pulsar is on average a relatively stable reservoir of matter. It stores material supplied by the companion, smooths out some of the short-term variations in the mass transfer rate, and delivers a more gradual flow of gas towards smaller radii. The timescale over which gas moves through the outer disk, often called the viscous timescale, can be much longer than the orbital period, ranging from days to months or more depending on the disk's properties. This means that changes in the rate at which the companion supply's mass may take considerable time to propagate inward. As a result, the outer disk acts as a buffer, mediating between the slower evolution of the binary and the more rapid processes that occur closer to the neutron star. In the context of a bursting pulsar, this outer accretion environment provides the essential setting in which matter first settles into ordered rotation around the neutron star. It is the region where chaotic inflow from the companion star transforms into a structured disk, where gravitational potential energy begins to be converted into heat and radiation in a controlled way, and where angular momentum is redistributed to allow matter to drift gradually inward. Observations of the outer disk through its optical and ultraviolet emission, through orbital modulations linked to hotspots and tidal features, and through long-term changes in brightness linked to variations in mass supply, all contribute to a coherent picture of how this environment operates. While many details of the microscopic physics remain active areas of research, the broad understanding of the outer accretion disk as a thin, rotating viscous structure is well established, providing a firm foundation for interpreting the behavior of the accretion flow in this region around the neutron star. Closer to the neutron star, the accretion disk changes character. The gas that has drifted inward from the outer regions now orbits at smaller radii where the gravitational pull is stronger and orbital speeds are higher. Each ring of material completes an orbit in a much shorter time than its counterparts further out, and the differential rotation becomes more pronounced. In this inner accretion disk, the density and temperature of the gas rise significantly compared with the outer parts, and the radiation it emits shifts toward higher energies. The material here has already lost a substantial fraction of its original angular momentum in order to move inward, yet it still retains enough to keep it from falling directly onto the neutron star. The balance between gravitational pull, centrifugal tendency, gas pressure, and magnetic forces is delicate, and under these conditions the flow becomes more vulnerable to instabilities that can concentrate matter, alter the rate of inward drift, and create the irregularities that later show up as variability in the emission from the bursting pulsar. The inner disk is still geometrically thin on average, but its vertical thickness grows somewhat relative to the outer regions, because the higher temperature causes the gas to puff up. At these radii, the energy released per unit mass as gas moves inward is much larger than in the outer disk, since the gravitational potential well steepens rapidly near the neutron star. Viscous dissipation and magnetic turbulence convert a growing fraction of the liberated gravitational energy into heat, raising the disk temperature to levels where it can emit strongly in ultraviolet and soft X-ray bands. The gas is highly ionized, meaning that electrons and ions move freely, and magnetic fields are tightly coupled to the plasma. This coupling drives the magnetorotational instability, a process in which small perturbations in the magnetic field and velocity grow over time, enhancing turbulence and greatly increasing the efficiency with which angular momentum is transported outward. The detailed microphysics of this instability involve complex interactions between magnetic tension, differential rotation, and fluid motions, and they are studied through numerical simulations. Observationally, however, the outcome is a disk where turbulent motions continually stir the gas, mixing hot and cooler regions and producing a fluctuating pattern of density and temperature on many scales. In principle, if the viscosity and heating in the disk were smooth and steady, the accretion flow would settle into a nearly constant pattern, with gas drifting inward at a rate that changes only slowly. In practice, the coupling between heating, cooling, and density allows instabilities to arise. One important class of such behavior is thermal instability. In certain ranges of temperature and density, A small increase in temperature can lead to a larger increase in heating than in cooling, causing that region to heat up even more, while a small decrease can lead to further cooling. Under these conditions, the disk cannot maintain a uniform state. Instead, it may separate into hotter, brighter patches and cooler, dimmer zones. Another related behavior is viscous instability, where changes in surface density alter the rate at which angular momentum is transported. Together, these processes can create cycles in which the inner disk alternates between phases of higher and lower accretion rate. In neutron star systems, such cycles can help set up the conditions for bursts by modulating how quickly fresh material is delivered to the surface. The inner disk also experiences the direct influence of radiation from the neutron star and from the innermost accretion regions. As gas falls deeper into the gravitational well and heats up further, it radiates more strongly. This radiation shines back on the disk, particularly on its inner rings, and can alter their temperature structure. In some regimes, strong radiation pressure can puff up the disk or drive winds that remove mass from its surface. Although the bursting pulsar may not reach the most extreme luminosities where radiation pressure completely dominates the feedback between emission and disk structure, still introduces additional ways for instabilities to develop. Regions that become slightly hotter can expand, changing their density and opacity, which in turn modifies how they absorb and emit radiation. Over time, this interplay between heating, cooling, and structure yields a complex pattern of brightness variations, many of which are smeared out by the turbulent nature of the flow, but some of which leave observable signatures in the rapid variability of the system. Clumping of matter in the inner disk is a natural outcome of these instabilities. Instead of a perfectly smooth distribution, the gas organizes itself into regions where surface density is modestly higher or lower than average. High-density clumps can move inward more efficiently under certain conditions, delivering short-lived surges of mass toward the neutron star. Lower-density regions, by contrast, represent channels where less material is available temporarily. The result is that the instantaneous accretion rate at the inner edge of the disk fluctuates around its long-term average. These fluctuations can be stochastic, producing irregular noise like variability in the light curve, or they can show quasi-periodic patterns if certain modes or oscillations in the disk are excited. Astronomers observe such variability in many accreting neutron star systems with power spectra that reveal broad noise components and in some cases narrow peaks associated with quasi-periodic oscillations. The precise origin of these oscillations remains an area of active research, with proposed contributions from disk oscillation modes, orbital motion near special radii, and interactions between the disk and the neutron star magnetic field. In all cases, the inner disk is recognized as a key site where these phenomena can arise. As gas moves inward through the inner accretion disk, its radial speed remains much smaller than its orbital speed, but it is larger than in the outer disk because the effective viscosity is greater and the density scale height is smaller. This means that the timescale over which matter moves from a given radius down to the inner edge can be much shorter here than in the outer regions, sometimes comparable to, or only slightly longer than the orbital period itself. As a result, changes in the conditions at these radii can propagate inward relatively quickly, translating local instabilities into variations in the supply of material that reaches the region where the disk terminates and the magnetosphere or boundary layer begins. The inner disk also provides a site where some of the gravitational energy released by accretion is channeled into non-thermal processes. Turbulent motions and magnetic reconnection events can accelerate particles to high energies, producing non-thermal radiation components such as hard X-rays. These components may vary differently from the thermal emission of the disk, adding further richness to the observed spectrum and timing behavior. The relative proportions of thermal and non-thermal emission in a given system depend on details of the disk structure, the strength and configuration of magnetic fields, and the overall accretion rate. While the broad outlines of these processes are understood, many specifics such as the exact geometry of coronal regions above the disk or the precise distribution of accelerated particles remain uncertain. In addition, the inner accretion disk must respond to the presence of the neutron star magnetic field even before the magnetosphere fully dominates the flow. Magnetic field lines emerging from the neutron star can thread the inner disk, exerting torques that either remove angular momentum from the gas or add it depending on the relative rotation rates of the star and the disk. These torques can truncate the disk at a certain radius and can also excite waves and warps in the inner regions. The location of this truncation radius where the disk effectively hands material over to magnetically controlled flow depends on the accretion rate and the strength of the magnetic field. Higher accretion rates push the truncation radius closer to the neutron star, while lower rates allow the magnetic field to dominate further out. As the accretion rate fluctuates due to the instabilities in the inner disk, the truncation radius can move inward or outward, changing the detailed configuration of the flow. This dynamic interaction between the inner disk and the magnetic field is particularly important for systems that exhibit bursts because it influences how and where material is funneled toward the surface, even though many details of this interaction remain uncertain and are the subject of ongoing observational campaigns and theoretical modeling. Overall, the inner accretion disk around the bursting pulsar is a region of heightened activity compared with the outer disk. Here, temperatures, densities, and magnetic field interactions combine to create a flow that is both more luminous and more variable. Instabilities in heating and angular momentum transport cause the gas to clump and fluctuate, leading to an accretion rate at the inner edge that is not perfectly steady, but instead wanders around its average value. Radiation from this region contributes significantly to the persistent high-energy emission of the system and carries imprints of the complex dynamics at work. At the same time, the inner disk continuously feeds material inward, delivering it as a time-varying flow that reflects the unstable processes operating in this region, close to the neutron star. Near the inner edge of the accretion disk, the ordered orbital flow of gas begins to encounter the immediate influence of the neutron star in a zone where conditions change rapidly over a relatively small distance. This region, often described as the boundary layer or impact zone, is where matter that has travelled inward through the disk must adjust from near-orbital motion to a state compatible with the rotation and magnetic environment of the compact object. In the inner disk, gas orbits at a speed close to the local circular velocity set by gravity, but the neutron star itself rotates at a different rate. The mismatch between these motions means that gas arriving at the innermost stable disk radius cannot simply continue on its previous trajectory. Instead, it must shed a final portion of its angular momentum, change its flow pattern, and convert much of its remaining orbital kinetic energy into heat and radiation. The way this happens depends on how strongly the neutron star magnetic field interacts with the inner disk. When the magnetic field is relatively modest, or the accretion rate is high, the disk can extend nearly to the solid surface of the neutron star. In this case, the boundary layer forms as a narrow, dense belt of gas that circles the star where the inner disk meets the stellar surface. Material in this belt decelerates from orbital speeds which can be a significant fraction of the speed of light to match the rotation of the star, which is fast but still slower than the orbital motion at the same radius. The resulting shear between layers moving at different speeds generates intense turbulence and strong viscous dissipation. In this process, the kinetic energy lost by the gas is converted into thermal energy, heating the belt to very high temperatures. The belt then radiates predominantly in X-rays, contributing a substantial fraction of the persistent high-energy emission from the system. The thickness, extent, and vertical structure of such a boundary layer are not yet fully known. Models suggest that it can spread over a significant fraction of the stellar surface near the equator, forming a bright hot region where newly accreted matter first settles. However, uncertainties remain about how far this zone extends toward higher latitudes, how deeply it penetrates below the visible surface, and how energy is transported within it. Some of the heat may be radiated quickly, while some is conducted inward or carried by convective motions deeper into the star. Observations of the spectrum and variability of the high-energy emission provide constraints on these details, but the underlying physics is complex and requires careful modeling. When the neutron star magnetic field is stronger, or the accretion rate lower, the disk does not reach all the way to the surface. Instead, magnetic pressure from the star's field balances the ram pressure of the inflowing gas at a certain radius above the surface. This distance, often called the magnetospheric radius, marks the point where the field begins to control the motion of the plasma. Outside this radius, the gas in the disk dominates the dynamics. Inside, the gas is forced to follow magnetic field lines. The boundary layer in this regime is not a simple belt at the stellar surface, but a more extended interface, where the disk plasma is gradually stripped of its angular momentum and channeled into funnel flows that follow field lines toward the magnetic poles or other preferred regions. In this magnetically truncated case, the impact zone is distributed along the field-guided paths where the flow ultimately strikes the stellar surface. At the truncation radius, gas in the inner disk feels a strong magnetic torque. Field lines that thread the disk can either spin up or spin down the gas depending on whether the disk rotates faster or slower than the magnetic pattern imposed by the neutron star. This interaction can form a complex boundary layer where gas piles up, forming a dense ring or inner wall before it is lifted from the disk and redirected along field lines. The process involves magnetic reconnection, turbulence, and shocks, which together dissipate energy and heat the plasma. As gas begins to follow the field, it accelerates along curved paths moving inward and downward toward the star. Along these trajectories, further collisions and compressions heat the material so that by the time it reaches the surface it is moving at high speed and carry a great deal of kinetic energy ready to be released in a final impact. The geometry of this magnetically mediated boundary region is three-dimensional and time-dependent. Field lines can be twisted by differential rotation between the star and the disk, and instabilities can cause the flow to switch between different channels or to become patchy rather than uniform. In some situations, matter may accumulate at the inner edge of the disk until local conditions allow a sudden episode of enhanced funneling onto the star, leading to short-term increases in accretion rate at the surface. These processes may contribute to variability in the persistent emission and can set the stage for more dramatic changes deeper into the precise connection between boundary layer behavior and the timing of bursts is still an area of active study. Across both weak and strong field regimes, the boundary layer represents a zone where gravitational potential energy is released at a very high rate, gas that falls from the inner disk radius down to the surface, or from the magnetospheric radius along field lines to the star spans a large drop in gravitational potential. The conversion of this energy into radiation makes the boundary region extremely luminous. In many neutron star systems, theoretical estimates indicate that a significant share of the total accretion luminosity arises here, comparable to or even exceeding the contribution from the disk itself. The radiation emitted in this zone emerges in a combination of thermal and non-thermal components. Thermal emission arises from hot dense gas close to local equilibrium, while non-thermal emission can result from Compton scattering, where energetic electrons in a hot corona upscatter, lower energy photons to higher energies. The detailed balance between these components depends on factors such as the density temperature and optical depth of the boundary layer, and on whether a corona of hotter, more tenuous plasma forms above it. Observations of bursting pulsars show spectra that often include both softer thermal components and harder tails, indicating that multiple emission regions and processes contribute. Time variability in the boundary layer further enriches the observational picture. As gas arrives from the inner disk or magnetospheric radius at a rate that fluctuates on short timescales, the luminosity and spectral shape of the impact zone can change accordingly. Rapid variations in density or temperature within the layer can produce flickering in the X-ray flux on timescales related to the local dynamical time and to the cooling time of the gas. Quasi-periodic oscillations, sometimes observed in the high-frequency power spectra of neutron star systems, may arise from oscillation modes in the boundary layer, from rotation of inhomogeneities within it, or from interactions between the layer and the underlying star. The exact origins of these features remain uncertain, but they underline the dynamic nature of this region. The boundary layer also serves as a mediator between the accretion flow and any outflows that the system may produce. Strong radiation from the impact zone can impart momentum to gas above the disk, potentially driving winds that carry matter away from the system. If the local luminosity approaches a level where radiative forces nearly balance gravity, even small increases in radiation can lift material off the surface or off the inner disk. Magnetic fields can also help channel some of the inflowing gas into outflows rather than letting all of it reach the star. These outflows reduce the net mass accretion rate and carry away angular momentum and energy, influencing the long-term evolution of the system. Observational signatures of such winds include absorption features in X-ray spectra that shift over time, suggesting the presence of ionized gas moving away from the neutron star. Despite the complexity of these processes, the essential role of the boundary layer in a bursting pulsar system is clear. It is the final stage in the accretion flow where matter transitions from the orbital motion of the disk to the conditions imposed by the neutron star's rotation and magnetic field. It is where much of the remaining gravitational energy is converted into heat and radiation, powering a large fraction of the persistent high-energy emission. It is also where fluctuations in the accretion rate and in the structure of the flow can have immediate consequences for how and where material arrives on the surface. From there, the newly accreted matter begins to spread and interact with layers already present on the star. But before that, deeper behavior is considered. The boundary layer stands as the crucial interface, where inflowing gas first encounters the immediate environment of the neutron star and releases energy in the intense impact zone that surrounds it. Surrounding the neutron star, an invisible but powerful structure extends far into space. The magnetosphere, the region in which the star's magnetic field dominates the motion of charged particles and guides the flow of plasma. Close to the neutron star, this magnetic field resembles that of a tilted dipole with north and south magnetic poles anchored in the solid crust and field lines that loop out into space before curving back to the surface. Further away, the field is distorted by rotation by the presence of the accretion disk and by currents that flow through the plasma, so the pattern becomes more complex than a simple dipole. Still, the basic idea holds that field lines provide paths along which particles move much more easily than across them, and that the configuration of these lines shapes where matter can travel and where radiation can escape. The magnetosphere co-rotates with the neutron star out to a characteristic distance, where the speed required to keep up with the star's spin would equal the speed of light. This boundary, often called the light cylinder, marks a transition region. Inside it, field lines try to rotate with the star dragging charged particles around and enforcing co-rotation. Outside it, field lines cannot remain rigidly locked to the star, because doing so would require parts of the field to move faster than light, which is not possible. As a result, some field lines open out into space, allowing plasma and electromagnetic energy to stream away along them. The exact shape and extent of the co-rotating region depend on the rotation rate and on how much plasma fills the magnetosphere. In a bursting pulsar that accretes matter, the magnetosphere is loaded with plasma drawn from both the accretion flow and from processes near the star's surface that create particle pairs. This plasma populates field lines with charges that move along them, forming currents that feed back on the magnetic field and modify its geometry. Within the magnetosphere, field lines divide into two broad classes: closed lines that loop back to the neutron star at both ends and open lines that extend outward without returning at least within the region where the field is controlled by the star. Closed lines dominate nearer the surface, creating a zone where particles can be trapped, bouncing or drifting along the loops. Open lines are concentrated near the magnetic poles, forming funnels through which outflows of relativistic particles and electromagnetic waves can escape. The boundary between closed and open zones is not a sharp physical wall, but a surface where field topology changes, and it plays an important role in organizing how energy and angular momentum leave the system. The strength of the magnetic field in the magnetosphere is immense. At the surface of a typical neutron star, the field can reach values billions or even trillions of times stronger than the magnetic field near Earth. As one moves outward from the star, the field strength drops roughly as the inverse cube of the distance for a dipole in vacuum. This steep decline means that close to the neutron star, the magnetic pressure is enormous, easily dominating other forces in the plasma, while further out gravity and gas pressure become relatively more important. In an accreting, bursting pulsar, the radius at which magnetic pressure and the ram pressure of the inward-flowing gas balance sets the magnetospheric radius. Outside this radius, gas in the disk largely controls its own motion, shaped by gravity and internal stresses. Inside it, the star's field forces plasma to follow its lines, disrupting the disk and funneling matter toward the surface. The magnetospheric radius is not fixed. It moves inward or outward depending on the accretion rate and the field strength. At high accretion rates, the ram pressure of the flow is large and can push the magnetospheric boundary closer to the neutron star, allowing the disk to extend further in. At lower accretion rates, the magnetic field can hold back the plasma more effectively, pushing the inner edge of the disk outward. This shifting boundary affects how and where gas couples to field lines and influences the balance between accretion and any outflows the magnetosphere may drive. In the region where disk and magnetosphere interact, field lines can thread the inner edge of the disk, linking the star's rotating magnetosphere to the differentially rotating plasma in the disk. These connections allow angular momentum to be exchanged between the star and the disk. If the inner disk rotates more slowly than the magnetic pattern anchored in the neutron star, the field can transfer angular momentum from the star to the disk, spinning the star down while spinning the disk up. If the inner disk rotates faster, angular momentum can flow in the opposite direction, spinning the star up. For many accreting neutron stars, the long-term evolution appears to approach a spin equilibrium, where the net torques balance over time, though short-term fluctuations in accretion rate can temporarily shift the system away from this balance. The details of these magnetic torques are still the subject of ongoing work, because the configuration of field lines and currents in the disk atmosphere is complex and not fully constrained by observations. Within the magnetosphere but outside the star itself, electric fields arise naturally from the motion of the magnetic field through space and from the presence of rotating charges. In certain regions, particularly along open field lines near the magnetic poles, and in gaps where charge density is insufficient to fully screen electric fields, these electric fields can accelerate particles to very high energies. Accelerated electrons and positrons follow curved field lines and emit radiation through processes such as curvature emission and synchrotron emission. This radiation can in turn produce further pairs of particles feeding a cascade that maintains the plasma population in the magnetosphere. The balance between electric fields, particle acceleration, and pair creation determines how much charged material is available to carry currents and shape the global field structure. Many aspects of these cascades remain uncertain because they involve microphysical processes that are difficult to model from first principles and to observe directly. The presence of an accretion flow modifies these classic magnetospheric processes compared with an isolated rotation-powered pulsar. The inflowing plasma adds mass and charge to the field lines, alters current systems and changes how open and closed regions are arranged. At the magnetospheric radius where disk and field meet, plasma can be lifted off the disk surface and guided along field lines. Some of this plasma flows inward, feeding the neutron star, while some may be directed outward along open lines, contributing to winds or jets that carry energy away. The coupling between disk and magnetosphere can also tilt or warp parts of the inner disk, changing the angle at which field lines intersect it, and further complicating the geometry. Inside the magnetosphere, plasma that follows closed field lines can form co-rotating clouds or streams that move with the neutron star's spin. These structures can affect how radiation produced near the surface or in the boundary layer escapes by absorbing scattering or reprocessing photons before they leave the system. For example, dense streams along certain lines of sight can periodically block or attenuate emission as the star rotates, while more tenuous plasma can imprint subtle energy-dependent features on the spectrum. Such effects need to be taken into account when interpreting the observed light curves and spectra of bursting pulsars, especially when trying to infer properties of the neutron star itself from its emission. At larger radii, open field lines carry away not only particles, but also electromagnetic energy and angular momentum. The magnetosphere thus acts as a channel through which the neutron star loses rotational energy over long timescales. Even in an accreting system where the star may be spinning up overall due to accretion torques, the magnetospheric outflow still removes some angular momentum. The balance between spin up from accretion and spin down from magnetospheric torques determines how the rotation rate evolves. In systems with moderate accretion rates and strong fields, this balance can lead to relatively stable spin periods, while in others the star may still be evolving toward an equilibrium. These processes are important because the rotation rate sets the timing pattern of any pulsations associated with the neutron star, and the field geometry determines how emission is beamed into space. Although core aspects of magnetospheric structure, such as the existence of closed and open zones and the general scale of the light cylinder, are well established in theory, many details remain under active investigation. The distribution of currents, the exact shape of the boundary between open and closed field regions, the spectrum and spatial distribution of plasma within the magnetosphere, and the time-dependent behavior of instabilities all introduce uncertainties. Observations of accreting neutron stars, including bursting systems, provide constraints on these properties through the timing and spectral features of their emission, but they do not yet fully pin down the microscopic physics. Numerical simulations that couple magnetohydrodynamics with radiation transport and particle acceleration are beginning to explore these regimes, but their resolution and physical fidelity are limited by computational resources. For the bursting pulsar, the magnetosphere stands as a global dynamic structure that links the neutron star to its surroundings. It sets the inner boundary of the disk, determines how matter is funneled from the disk to the surface, defines the regions where outflows and winds can form, and shapes the pathways along which high-energy radiation travels outward. Against this magnetic framework, rapid processes nearer the surface and in the accreted layer unfold, but the large-scale field and its magnetosphere provide the overarching environment within which those processes take place, controlling how energy and angular momentum move through the system, and how the presence of the neutron star is imprinted on the surrounding space. Within the reach of the neutron star magnetic field, the motions of plasma and the pattern of radiation together produce the pulses and bursts that define the observable character of the bursting pulsar. The magnetosphere and the field-guided flow from the inner accretion regions act as a structured lantern, shaping high-energy emission into beams that sweep through space as the star rotates. The magnetic axis is not generally aligned with the rotation axis, so regions of enhanced emission near the magnetic poles trace out circular paths in the sky. When one of these beams crosses the line of sight to a distant observer, the system appears bright. When it swings away, the observed flux declines. This repeated pattern of brightening and fading imposed by the spin of the neutron star gives rise to the regular pulses that mark the rotation period. In an accreting system, much of this emission originates where magnetically funneled plasma strikes the surface near the magnetic poles, and where hot gas in the boundary layer and magnetosphere radiates. The beams are not sharply defined edges, but broad patterns shaped by the geometry of the field, by the distribution of hot plasma, and by the effects of strong gravity on the paths of photons, which can bend light around the neutron star enough to keep emitting regions in view for longer fractions of a rotation than would be expected in ordinary space. The result is a pulse profile that can be smooth or structured, sometimes showing multiple peaks or shoulders within a single rotation. This profile changes with photon energy because different processes and regions contribute more strongly at different energies, and because scattering in the magnetospheric plasma can redistribute photons in direction and energy. The persistent pulsations seen when the system is not bursting provide a continuous probe of the spin rate and of the large-scale magnetic geometry. By measuring the times of arrival of pulses over long intervals, astronomers derive a precise rotation period and track how it evolves. Small changes in this period reflect torques applied by the accretion flow and by the magnetospheric outflow. When the accretion rate is higher, the accretion torque can spin the neutron star up, shortening the period slightly over time. When the accretion rate declines, or when magnetospheric spin-down dominates, the period can lengthen. Superposed on these long-term trends are fluctuations related to changes in the flow near the magnetospheric radius, which alter how angular momentum is exchanged. By fitting models to the timing data, researchers infer parameters such as the strength of the magnetic field, the average accretion torque, and the possible presence of additional variations due to processes within the magnetosphere. Against this backdrop of persistent pulses, the bursting behavior stands out as sudden sharp increases in high-energy emission that occur at irregular intervals. During a burst, the flux in X-rays can rise by large factors above the persistent level in a short time, often within a few seconds, and then decay on a timescale that may range from several seconds to longer intervals depending on the system and the accretion rate. These bursts recur in complex patterns. In some episodes, they come in rapid succession with relatively short waits between events. In others, they are more widely spaced, separated by quiet intervals during which the system returns to its persistent state. The light curves of these bursts often show fast rise and slower decay, a characteristic shape that indicates a sudden release of stored energy, followed by radiative cooling and readjustment of the flow. The detailed pattern of bursts, including their durations, separations, and peak fluxes, encodes information about how the accretion environment reorganizes itself. In a bursting pulsar, many lines of evidence point to the magnetospheric region and the inner accretion flow as the primary sites where this storage and release of energy occur. One broadly discussed picture is that instabilities in the coupling between the inner disk and the magnetosphere allow matter to accumulate in a reservoir near the magnetospheric radius, and then to be dumped inward in episodes when local conditions cross a threshold. In this view, when the accretion rate from the outer disk onto the inner edge exceeds the rate at which matter can be funneled along field lines to the surface gas piles up, the magnetospheric boundary gradually shifts and pressure builds. Once a critical point is reached, additional plasma can force open channels into the magnetosphere, leading to a surge of material along field lines toward the neutron star. This sudden increase in inflowing mass raises the luminosity, producing a burst. After the reservoir is depleted, the flow subsides. The luminosity drops back toward the persistent level, and the cycle begins again as the disk refills the inner region. While this scenario captures many observed features, important details remain uncertain, including how exactly the threshold is set, how the geometry of the field and disk drive the accumulation and release, and how rapidly the system transitions between states. Observations show that bursts can alter the pulse profile and the phase-dependent flux. During a burst, the amplitude of the pulsations often changes, either increasing, because emission from accretion columns at the magnetic poles brightens, or decreasing if additional more isotropic emission from an expanded impact region dilutes the pulsed fraction. Sometimes the shape of the pulse profile shifts with peaks moving slightly in phase or changing their relative heights. These changes indicate that the spatial distribution of emission on and near the neutron star has been modified. For example, if the inflowing material during a burst spreads the emitting region to wider areas around the magnetic poles, the beaming pattern can become broader and less sharply modulated by rotation. If hot plasma fills more of the magnetosphere, scattering can smooth out angular contrasts. By analyzing how the pulse profile evolves through the rise and decay of bursts, astronomers extract clues about how the magnetosphere and funneled flows respond to sudden changes in accretion rate. Bursts also reveal themselves in the energy spectrum. The increased luminosity during an event is often accompanied by changes in spectral shape, such as a shift toward higher effective temperatures in the thermal components, or a strengthening of hard tails associated with Compton upscattering in hot plasma. These spectral changes vary over the course of a burst. Early in the rise phase, the spectrum may harden quickly, as a flood of high-energy photons emerges from shocked and compressed gas near the impact region. During the decay, cooling causes the spectrum to soften gradually. The magnetospheric environment, with its strong field and population of energetic electrons, plays a central role in shaping these spectral changes by determining where photons are produced and how they scatter before escaping. In some bursts, rapid quasi-periodic modulations can be seen superposed on the overall light curve, sometimes at frequencies related to the neutron star spin, or to characteristic timescales in the inner flow. These modulations may reflect oscillations in the funneled accretion stream's vibrations of the magnetospheric boundary or wave modes in the plasma near the field lines that guide inflow. However, their precise origin remains uncertain, and multiple mechanisms may operate in different bursts or at different times. What is clear is that the magnetosphere is not static during bursts. It responds dynamically to changing mass loading and to the intense radiation fields occasionally entering regimes where coherent or semi-coherent oscillations can develop and imprint themselves on the emitted signal. The bursts are described as erupting without warning, because in many systems their onset times are not perfectly predictable. While the overall pattern of bursts may correlate with the average accretion rate, and while certain statistical regularities can be measured, individual events are not preceded by easily detectable, long-term precursors in the persistent emission. The instabilities that trigger them arise from local conditions in the inner disk and magnetosphere that cannot yet be fully monitored or modelled. As a result, the bursting pulsar appears to alternate between quiet intervals in which it emits steady pulses and sudden episodes where these pulses ride atop a bright transient flare. From afar, the light curve looks like a sequence of regular beats, interrupted by irregular surges reflecting how the magnetospheric environment transitions between quasi-steady and unstable states. Over longer timescales, the behavior of pulses and bursts provides a way to map the global magnetospheric evolution. Changes in the spin period and its derivative reveal how the average torque from accretion and outflow shifts. Changes in the pulse profile shape and energy dependence indicate reconfigurations in the beaming geometry or in the distribution of emitting plasma. Changes in burst recurrence time and strength trace how the inner disk and magnetosphere share the task of transporting mass inward. By combining these strands, astronomers build models of the magnetosphere as a living structure that both channels and regulates accretion. Some aspects of these models are well established, such as the basic dipolar nature of the field near the star and the importance of field-guided funnel flows for producing pulsations. Others remain ambiguous, including the detailed maps of currents and plasma densities, the conditions for onset of instabilities, and the precise links between bursts and changes in the magnetospheric radius. Numerical simulations that couple three-dimensional magnetohydrodynamics with radiation transport can now reproduce some features of accretion onto magnetized stars, but they still operate with simplifications and limited resolution. For the bursting pulsar, the observed pulses and bursts thus serve as both a diagnostic and a reminder of these uncertainties. The pulsations show that the magnetosphere is stable enough on average to maintain a coherent beaming pattern. The bursts show that this stability is punctuated by episodes of rapid reconfiguration, where the coupling between disk and field allows stored material and energy to be released in sudden bright events. Together, pulses and bursts trace the complex interplay between rotation magnetic fields and accretion in the outermost layers of the neutron star environment, setting the stage for the behavior of matter once it reaches the surface and begins to interact with the star's gravity and crust. At the neutron star surface, gravity and motion combine to create conditions unlike those on any ordinary star. The bursting pulsar is only about the size of a city, yet it holds more mass than the Sun. This means that the gravitational field at its surface is immensely strong. A small object placed just above the surface would feel a pull that is many billions of times stronger than the gravity at the surface of Earth. In such an environment, even light finds its path bent. Photons that emerge from the surface climb out of a deep gravitational well, losing energy as they go. Their wavelengths stretch, shifting the radiation toward lower energies in a process known as gravitational redshift. To a distant observer, light that is born at a certain energy near the surface appears slightly softer after it has climbed away. The curvature of space-time around the neutron star is strong enough that light emitted from the far side can be bent around the star and still reach an observer. As a result, more than half of the surface is visible at once from any given direction. Emitting regions that would hide behind the limb in flat space remain partly in view here. This bending shapes the apparent size and brightness of hotspots and belts on the surface, and helps determine how the pulses from the bursting pulsar look when recorded by telescopes. The surface itself is not a bare solid crust exposed directly to space. Instead, a very thin atmosphere of plasma overlays the solid layers. This atmosphere is only a few centimeters deep in many models, yet it plays a crucial role in shaping the emergent radiation. Under the intense gravity, the pressure rises steeply over a very small height, and the density at the base of the atmosphere is high. The temperature in this region is also high, often many millions of degrees, at locations where accretion is active, so atoms are highly ionized. Electrons and ions move freely and the gas behaves as a hot plasma. Radiation and matter in this layer are tightly coupled. Photons scatter many times before escaping, and their energies and directions are redistributed by interactions with electrons and ions. The strong magnetic field of the neutron star threads this atmosphere, quantizing the motion of charged particles and making the properties of the plasma different along and across the field lines. These effects cause the atmosphere to emit radiation with a spectrum that deviates from a simple black body, and with a beaming pattern that favors certain directions over others. The spin of the neutron star adds another layer of complexity. The bursting pulsar rotates rapidly, completing a full turn in a time that is often measured in fractions of a second or a few seconds. At the equator, the surface moves at a significant fraction of the speed of light. This rotation flattens the star slightly, making it oblate rather than perfectly spherical, and introduces relativistic effects such as Doppler boosting and aberration. Regions of the surface that move toward an observer beam, their radiation slightly appearing brighter, and with photons shifted to higher energies, while regions moving away appear slightly dimmer and softer. As the star turns, these effects modulate the observed flux and spectrum, even if the underlying temperature pattern on the surface remains constant. In reality, the temperature is not uniform across the neutron star. Accretion from the magnetosphere deposits fresh matter and energy, preferentially near the magnetic poles or along belts, where the boundary layer meets the surface. These areas become hotter than the surroundings, forming bright spots or zones that dominate the high-energy emission. Outside these hotspots, the surface may still be warm due to the internal heat of the star and past accretion, but it emits more gently. The contrast between hot and cooler regions combined with the rotation and gravitational light bending shapes the observed pulsations. The pattern is dynamic rather than static, because as material continues to arrive and spread, the local temperature adjusts and the brightness of each region evolves over time. Newly accreted matter does not simply stop at the point where it first strikes the surface. Guided by the magnetic field or by the geometry of the boundary layer, plasma impacts the crust with high speed, then decelerates abruptly, releasing kinetic energy as heat. The heated material and underlying layers respond by expanding slightly and by driving flows along the surface. In some models, the inflowing gas forms a spreading layer that wraps around the star near the equator, slowing as it moves and sharing its angular momentum with the underlying crust. In others, accretion columns near the poles channel matter to more localized regions. In both cases, the extreme gravity confines the flow to a very thin layer close to the surface. Even modest vertical motions are quickly damped. Horizontal motions, however, can be swift as gas tries to redistribute and share the deposited energy. The rate at which this redistribution occurs depends on factors such as viscosity, magnetic coupling, and the thermal conductivity of the outer crust. Under the intense conditions at the surface, the concept of a firm, rigid boundary between atmosphere and solid layers becomes nuanced. The outermost part of the crust consists of nuclei packed into a dense lattice, immersed in a sea of electrons. The pressure is so high that distances between nuclei are much smaller than in ordinary solids. Above this lattice sits the atmosphere. Below it, matter becomes denser and more exotic. At the surface, the crust supports the weight of the atmosphere and of any accreted layers, and it responds elastically to changes in load. Over long time scales, repeated accretion and bursting can alter the chemical composition of this outer crust as fresh nuclei arrive and are compressed. However, these deeper changes belong to the behavior of the crust and interior. From the perspective of the surface itself, the immediate effect of accretion is to change the local pressure, temperature, and composition in a layer that remains extremely thin compared with the star's radius. Any motion in this environment happens against a background of crushing gravity. The energy required to lift material even a few centimeters above the surface is large compared with many other energy scales. This means that convection, if it occurs, must work within narrow vertical ranges. Heat tends to flow more easily sideways or downward than upward. As a result, the emergent radiation is sensitive to slight changes in surface composition, magnetic field, strength, and local heating, because these factors determine how easily photons can escape. During bursts, when intense radiation is produced deeper in the accreted layer, the surface atmosphere must carry this flux outward without becoming unstable. In many events, the radiation remains below the level where it can lift the atmosphere significantly against gravity, so the surface does not expand much. In others, especially in different systems not limited to this bursting pulsar, brief episodes of expansion can occur when radiation pressure locally approaches balance with gravity. For the bursting pulsar described here, the interplay between surface gravity and radiation sets an upper limit on how bright the burst can appear before the atmosphere begins to respond dynamically. The surface also serves as the interface where high-energy particles from the magnetosphere deposit their energy. Electrons and ions accelerated along field lines can strike the atmosphere, heating it and producing aurora-like features in principle, though under conditions far more extreme than any aurora on Earth. These particle impacts contribute to the overall heating of certain regions and can modify the local ionization state and composition. In practice, disentangling the effects of particle bombardment from those of accretion outflow is challenging because both processes may occur in overlapping locations. Still, the combined picture is that the neutron star surface is constantly bombarded by energy and matter arriving from above, while at the same time it radiates energy away into space and conducts heat into deeper layers below. Observationally, the surface of the bursting pulsar is not seen directly in visible light. Instead, its presence is inferred through high-energy photons that originate in the hot atmosphere and boundary layer. By fitting models of neutron star atmospheres to observed X-ray spectra, astronomers attempt to infer surface temperatures, emitting areas, and gravitational redshifts. These inferences carry uncertainties because they depend on assumptions about the composition of the atmosphere, the strength and geometry of the magnetic field, and the distribution of hotspots. Yet over time, observations of many systems, including bursting pulsars, support a picture in which surface gravity is extremely strong. Radii are on the order of several tens of thousands of meters, and masses are comparable to or greater than that of the Sun. For the bursting pulsar, the surface and its gravity act as the final stage in the journey of accreted matter from the companion star. Gas that has travelled through the disk crossed the boundary layer and followed magnetic field lines now comes to rest in a shallow layer atop the crust. There it experiences conditions of pressure and temperature that surpass those found in ordinary stars. Gravity confines it tightly, while the surface radiates away the energy of its arrival. Over time, this accumulated material forms a distinct layer with properties shaped by the balance between accretion radiation and thermal conduction. The detailed behavior of that accreted layer, including how it stores and releases energy in bursts, belongs to the structure beneath the visible surface. For now, the focus remains on the surface itself, as a place where extreme gravity shapes every motion, and where radiation emerging from the atmosphere carries the imprint of these conditions out into space, making the bursting pulsar observable as a compact, rapidly rotating beacon, whose surface, though never directly seen, governs the character of its high-energy light. Over time, the steady rain of matter from the accretion flow builds a distinct layer of fresh material on top of the neutron star crust. This accreted layer sits just beneath the thin atmosphere and above the denser solid regions, forming a shell that is shallow in thickness, yet enormous in mass compared with familiar surfaces. Gas that has travelled through the magnetosphere and boundary layer now comes to rest here, compressed by the immense gravity into a structure where pressure and density climb rapidly with depth. Near the top of the layer, conditions are still relatively gentle by neutron star standards. The plasma is hot and fully ionized with nuclei and electrons moving freely, but the density is low enough that radiation can escape on timescales shorter than the time needed for matter to drift downward. Deeper in the weight of overlying material squeezes the plasma into a more compact state, increasing its density and pressure. Each parcel of newly arrived gas begins at the surface and gradually sinks as more matter piles on above, carrying its composition and thermal energy into the interior of the layer. The composition of this accreted shell reflects the material supplied by the companion star and the processing it undergoes as it is compressed and heated. If the companion resembles a normal star, the gas that arrives at the neutron star surface is rich in hydrogen and helium elements that can fuse into heavier nuclei under the right conditions. As matter sinks deeper into the layer, temperature and pressure become high enough to ignite nuclear reactions in a controlled way. Hydrogen burning transforms hydrogen into helium. Helium burning can produce heavier elements such as carbon and oxygen. The rate at which these reactions proceed depends on local temperature, density and composition. If the heating from accretion and nuclear burning is balanced by cooling through radiation and conduction, the burning can remain stable, steadily converting fuel into heavier nuclei as fresh material arrives. In other regimes, the balance is more delicate, and nuclear reactions can become unstable, leading to sudden thermonuclear flashes. In many accreting neutron star systems, such flashes manifest as thermonuclear bursts, rapid increases in X-ray brightness, powered primarily by runaway nuclear burning in the accreted layer. In those cases, matter accumulates until a critical combination of temperature and pressure is reached at some depth. Small fluctuations in conditions can then trigger a runaway, because nuclear reaction rates rise steeply with temperature. Once ignited, burning spreads rapidly across the star, releasing a large amount of energy on a short timescale. The emergent radiation heats and expands the outer parts of the layer and atmosphere, producing a burst with a fast rise and slower decay as the burning exhausts its fuel and the layer cools. Observations of such bursts in some systems show characteristic spectral evolution and energy output that match this thermonuclear picture. For the class of systems known as bursting pulsars, however, the situation appears more complex. Many observed bursts in these objects have properties that suggest a significant contribution from rapid changes in the accretion rate, rather than being powered solely by nuclear burning. The overall energy released in individual bursts, the relation between burst strength and persistent emission, and the presence of pulsations linked closely to accretion geometry all indicate that instabilities in the flow near the magnetospheric radius and boundary layer play a central role. In this accretion-driven picture, matter builds up in a reservoir near the inner disk edge, then is suddenly channeled inward in a brief episode of enhanced accretion. At the surface, this corresponds to a sudden increase in the rate at which fresh material arrives on the accreted layer, raising the heating rate and boosting the luminosity. Gravity ensures that nearly all of the gravitational potential energy released by this additional inflow is converted into heat and radiation in the outermost layers. The accreted shell responds by brightening and by adjusting its temperature profile, but the underlying mechanism remains tied to how matter is delivered rather than to an internal thermonuclear runaway. Distinguishing between purely accretion-driven bursts and bursts with a strong thermonuclear component requires careful analysis of spectra light curves and recurrence patterns. In bursting pulsars, evidence points to a combination of effects. Gravitational energy from accretion provides a dominant contribution in many events, while nuclear burning may proceed mostly in a stable or mildly unstable manner, adding extra heating without fully dominating the observed burst. Some sources in this class show occasional bursts whose properties more closely resemble thermonuclear events, suggesting that under certain conditions the layer can still undergo runaway burning. However, uncertainties remain, and the exact balance between accretion instabilities and nuclear ignition in each system is not yet fully established. The accreted layer is therefore best viewed as a dynamic system that both responds to and participates in the broader accretion cycle. As matter accumulates, the layer grows thicker and heavier. Heat from accretion from nuclear burning and from deeper interior processes flows through it. At any given depth, the temperature and composition reflect the entire history of accretion, not just the most recent inflow. When an accretion-driven burst occurs, the sudden increase in mass inflow and luminosity perturbs this structure. The outer parts of the layer heat up, the atmosphere brightens, and the vertical temperature gradient steepens. In response, enhanced radiative diffusion and possibly convective motions carry energy both upward to be radiated away and downward into deeper layers. After the burst, the layer cools toward a new equilibrium, but its detailed structure is no longer the same as before. Over many bursts, this repeated cycle of heating and cooling gradually alters the composition and thermal state of the accreted shell. Nuclear reactions during and between bursts convert light elements into heavier ones, building up ashes that sink toward the base of the layer. These ashes change the equation of state thermal conductivity and heat capacity of the material, influencing how future heating episodes propagate. At the same time, continued accretion from the companion replenishes the outer part of the shell with fresh fuel. The layer thus develops a stratified structure, lighter elements near the top, intermediate products at moderate depths, and heavier nuclei approaching the boundary with the underlying crust. The details of this stratification, including the exact composition and thickness of each zone, depend on the long-term accretion rate, the nuclear reaction pathways followed, and the relative importance of stable versus unstable burning. Many aspects of these processes remain uncertain. Nuclear reactions in dense hot matter involve networks of many possible pathways, and reaction rates for some key steps are not yet measured precisely in laboratory conditions. The presence of strong magnetic fields complicates the microphysics by modifying the behavior of electrons and ions. Mixing processes such as convection and shear-driven turbulence can blend material across different depths, altering the composition profile. Neutrino emission from dense regions can carry energy away, changing how heat is stored and transported. The result is that theoretical models of the accreted layer must make approximations, and different assumptions can lead to different predictions for when and how bursting behavior occurs. Observations of bursting pulsars provide constraints, but they do not yet fully resolve all ambiguities, especially because multiple physical mechanisms can produce similar signatures in light curves and spectra. Despite these uncertainties, several broad conclusions are robust. The accreted layer is thin compared with the radius of the neutron star, yet it is thick enough in terms of pressure and column depth to store substantial fuel and to hold significant thermal energy. It is constantly renewed by accretion, with fresh material arriving at the top and older material being compressed toward the bottom. It sits at the interface between the outer accretion environment, which supplies mass and energy from above, and the solid crust which supports the layer from below and conducts heat into the interior. Bursts, whether primarily accretion-driven or aided by thermonuclear burning, represent episodes in which the usual balance of inflow, storage and release is temporarily disturbed, allowing energy to emerge more rapidly than in the persistent state. After each burst, the layer must redistribute its internal energy and composition before the next event begins. In the long view, the accreted shell on the bursting pulsar is not a static coating, but a living structure that tracks the history of the system. Its thickness, temperature profile and composition evolve over timescales that range from the intervals between bursts to the much longer intervals over which the average accretion rate may change. Each short burst that appears as a brief spike in the light curve corresponds to a more extended episode of adjustment within this layer, as matter and heat find new equilibrium under the unchanging pull of the neutron star's gravity. The details of that adjustment shape how the burst in process proceeds, set the conditions at the top of the crust, and provide a bridge between the observable high-energy emission and the deeper interior where matter is compressed beyond the densities and states accessible in the accreted shell. Beneath the accreted layer that has built up on the bursting pulsar, the outer part of the neutron star itself forms a solid crust, a rigid structure where matter is compressed into forms that do not appear in ordinary planets or stars. This crust begins just below the depth, where the accreted shell becomes too dense and cold to behave like a fluid layer, and extends inward for a distance of a few kilometers, though its exact thickness depends on the mass and radius of the neutron star. In this region, nuclei arrange themselves into a dense lattice, a repeating pattern somewhat like the ordered structure in a crystal, but packed far more tightly than any crystal on Earth. Electrons move freely through this lattice, forming a degenerate gas, a state in which quantum effects and the Pauli principle determine how particles fill available energy levels. The pressure in the crust is provided mainly by these electrons, which resist further compression, not because of thermal motion, but because quantum rules do not allow them all to occupy low-energy states. As depth increases, the weight of the overlying material squeezes the lattice and electron gas to ever higher densities. Near the top of the crust, where the pressure is relatively modest by neutron star standards, the nuclei resemble those found in dense white dwarf stars, mostly elements near iron and nickel, together with the ashes of nuclear burning in the accreted layer. These ashes produced when hydrogen and helium fuse into heavier nuclei during stable burning, and any thermonuclear flashes are carried downward as new material arrives from above. As they sink, the rising pressure and density change their internal structure. Electrons are forced into nuclei, a process known as electron capture, which converts protons into neutrons and gradually drives the composition toward more neutron-rich species. Each capture releases energy in the form of neutrinos and heat, adding to the thermal budget of the crust. At certain depths, these reactions occur at specific pressures and densities, forming a sequence of layers where composition changes step by step, as matter is driven to more neutron-rich states. Deeper in the crust, the density becomes so high that neutrons begin to leak out of nuclei, forming a sea of free neutrons that coexists with the remaining nuclear lattice. This transition, often called neutron drip, marks the boundary between the outer crust, where all neutrons are bound inside nuclei, and the inner crust, where free neutrons are present. In the inner crust, nuclei become highly neutron-rich, and are immersed in a background of degenerate electrons and free neutrons. The presence of this neutron fluid alters the mechanical and thermal properties of the material. Free neutrons can move more easily than nuclei, and under some conditions they form a superfluid, a quantum state, in which they flow without friction on large scales. The lattice of nuclei, meanwhile, continues to provide rigidity, allowing the crust as a whole to support shear stresses, while the neutron fluid threads through it. The precise arrangement of matter in the inner crust at the highest densities is not fully known. Many theoretical models suggest that as density approaches values near those found deeper in the interior nuclei, may deform into elongated or flattened shapes, forming structures sometimes described as resembling rods, slabs, or more complex geometries. These configurations, collectively nicknamed pastorfaces, would arise because of a competition between nuclear forces which favour dense clumps of matter and Coulomb forces which favour more diffuse distributions. Whether such phases truly exist, and if so, over what range of densities and temperatures, remains uncertain and depends on details of the nuclear interaction that are not yet fully constrained by experiment. Observationally, the inner crust is not directly visible, but its presence affects how the neutron star responds to stresses and how heat moves through the star, so models of bursting pulsars must consider these possibilities, even while acknowledging the remaining uncertainties. The crust as a whole plays a central role in the thermal evolution of the bursting pulsar. Heat deposited at the surface by accretion and bursts, and heat generated within the crust itself by electron captures and other nuclear reactions must be conducted both outward toward the surface, where it can be radiated away, and inward toward deeper layers. The efficiency of this conduction depends on the composition, the arrangement of the lattice, the presence of impurities, and the behavior of electrons and neutrons. Electrons are the primary carriers of heat in much of the crust, moving through the lattice and transporting energy. If the lattice contains many impurities or irregularities, electron scattering increases, reducing thermal conductivity and causing heat to remain localized for longer. If the lattice is more regular, heat spreads more quickly. The neutron fluid in the inner crust can also contribute to heat transport under some conditions. Because the crust sits between the hot accreted layer and the denser core, it acts as a thermal buffer. During periods of high accretion, such as extended episodes when the bursting pulsar remains bright for months or years, heat can seep into the crust and raise its temperature. When accretion slows or stops, the crust cools back toward equilibrium with the interior. Observations of some neutron stars after long outbursts show this cooling directly as the X-ray luminosity declines on timescales of years, tracing how heat diffuses out of the crust. These crust cooling curves provide important clues about the thermal conductivity and heat capacity of crustal matter. In bursting pulsars, individual bursts are shorter and less energetic than such long outbursts, but repeated bursts over time still deposit heat. The cumulative effect of many bursts combined with steady accretion shapes the temperature profile of the outer crust. The crust also bears the mechanical stresses imposed by rotation magnetic fields and the continual addition of mass from above. As the bursting pulsar accretes, its total mass increases slightly, and its radius may shrink a little, changing the gravitational field. The rotation rate can also evolve as torques from accretion and magnetospheric outflows spin the star up or down. These changes alter the equilibrium shape of the neutron star. For example, a faster rotating star is more oblate while a slower one is closer to spherical. The rigid crust must adjust to these changes. When the required adjustment is gradual, the crust can deform elastically. When stresses exceed the elastic limit, the lattice may fracture or undergo sudden rearrangements in events sometimes described as starquakes. In rotation-powered pulsars, such sudden adjustments have been invoked to explain abrupt changes in spin rate known as glitches. In accreting systems like bursting pulsars, the situation is more complex because ongoing accretion and magnetic interactions also affect the spin, but the crust still carries stresses that may occasionally be relieved in localized failures. If such failures occur, they can release energy, alter the magnetic field configuration anchored in the crust, and possibly influence accretion flows. However, the detailed connection between crust fractures and observable events in bursting pulsars remains uncertain, and current evidence does not yet allow firm conclusions about how often such events happen, or how strongly they affect bursting behavior. Another important role of the crust is to anchor the magnetic field. Over long timescales, the magnetic flux of the neutron star is thought to be tied to currents that flow in the crust and in deeper layers. As accretion proceeds and fresh material covers the surface, the outer parts of the field can be distorted or buried. Conducting material flowing over the surface can drag field lines with it compressing or screening them. Over time, some field lines may diffuse outward again while others remain buried. This evolution affects the strength and geometry of the field at the surface and in the magnetosphere, which in turn alters how the accretion flow is channeled and how pulses and bursts are produced. Observations of accreting neutron stars suggest that long-term accretion can reduce the apparent surface field strength compared with isolating pulsars, although the degree and mechanisms of this reduction are still under study. In bursting pulsars, the crust therefore participates indirectly in setting the magnetic environment through its role as a conductor and anchor for the field. Bursts themselves can leave lasting imprints on the crust. When a burst occurs, a large amount of energy is released in a short time at or near the top of the accreted layer. Some of this energy escapes immediately as radiation, but some is conducted downward into the underlying crust. This extra heat temporarily raises the local temperature. Over time, it diffuses deeper and sideways, altering the thermal structure. If bursts recur frequently, the crust may maintain a higher average temperature than it would under steady accretion alone. A warmer crust has different mechanical properties and different rates of nuclear reactions compared with a cooler one. For example, certain pycnonuclear reactions, which involve fusion triggered by high density, rather than high temperature, can proceed at different rates depending on the local conditions. These deeper processes contribute additional heat and can influence how the crust cools between bursts and over longer intervals. Many of these reaction rates are uncertain, and the precise balance between heating by nuclear processes and cooling by neutrino emission and conduction is still being refined in theoretical models. In observational terms, the influence of crustal heating by bursts appears indirectly through subtle changes in the persistent emission and through long-term trends in the thermal state of the neutron star. By comparing observations with models that include detailed crust physics, astronomers attempt to infer properties such as the composition of the crust, the presence of neutron superfluidity, and the efficiency of heat transport. However, multiple combinations of parameters can often reproduce the same data within current uncertainties, so the picture remains incomplete. Even so, it is clear that the crust of the bursting pulsar is not a passive foundation. It is an active participant in the system's evolution, responding to accretion nuclear reactions and bursts by adjusting its temperature composition and stress state. It supports the overlying accreted layer conducts heat between surface and interior anchors, the magnetic field, and resists or yields to mechanical stresses imposed by changing rotation and accretion flows. All of these roles feed back into the observable behavior of the neutron star. The bursts that appear as brief flashes in the light curve are connected through the accreted layer to deeper processes in the crust that unfold over much longer timescales. The interplay between these layers under the constant influence of the star's gravity shapes the environment through which matter must pass on its way toward the yet denser regions further inside, where the nature of matter itself becomes more uncertain than anywhere else in the system. Far below the crust of the bursting pulsar, matter reaches densities where familiar descriptions lose their clarity, and the behavior of particles is governed by conditions that cannot be reproduced in any laboratory on Earth. As depth increases past the base of the inner crust, the last vestiges of a lattice of nuclei dissolve, and the material transitions into what is commonly called the core, a region that occupies most of the neutron star's volume and contains most of its mass. In the outer core, matter is thought to be composed primarily of neutrons with a smaller fraction of protons, electrons, and muons arranged in a nearly uniform fluid. The density here is comparable to and then greater than the density inside an atomic nucleus. Pressure is supported by the quantum mechanical degeneracy of neutrons, and by their strong interactions which resist further compression. The distinction between individual nuclei disappears. Instead, neutrons and protons are packed together in a continuous medium where the strong nuclear force and the Pauli principle determine how particles arrange themselves. Under these conditions, the temperature of the core is high in absolute terms, hundreds of millions of degrees or more, yet low, compared with the characteristic energies set by degeneracy and nuclear interactions. As a result, the core behaves as a cold quantum fluid rather than as a hot classical gas. Many theoretical models indicate that neutrons in the outer core form a superfluid, a state in which they pair up and move collectively, while protons form a superconducting component. In such a state, rotation is carried by quantized vortices, narrow tubes around which the superfluid circulates, and magnetic fields thread the superconducting protons in quantized flux lines. The arrangement and motion of these vortices and flux tubes influence how the neutron star responds to changes in spin and to external torques. When the star is spun up by accretion, as in a bursting pulsar, angular momentum must be transferred from the accreted matter to the core. This transfer proceeds through the motion of vortices which can pin to the crust or to structures within the core and then unpin in sudden events. In some rotation-powered pulsars, such motions have been invoked to explain abrupt changes in spin rate known as glitches. In accreting systems, the interplay between superfluid vortices, superconducting flux tubes, and the crust is more complicated, and the extent to which similar events occur remains under investigation. What is clear is that the core's superfluid and superconducting nature affects how quickly the star can adjust its rotation to match the torques applied by accretion and magnetospheric outflows, and how internal friction and coupling distribute angular momentum between different layers. The core is also the primary site of neutrino emission in the neutron star. Neutrinos are nearly massless particles that interact only weakly with matter, allowing them to escape freely from dense regions and carry energy away. In the outer core, various neutrino-producing reactions can occur. One set of processes, often called modified beta reactions, proceeds when neutrons convert to protons and electrons, or vice versa, in interactions that also involve a bystander nucleon to conserve momentum. These reactions, known collectively as modified Erka processes, remove energy at a rate that depends sensitively on temperature. In some cores, if the proton fraction and other conditions satisfy certain criteria, more direct beta reactions without a bystander are possible. These direct processes remove energy far more efficiently, leading to faster cooling. Whether direct neutrino emission operates in a given neutron star depends on details of the dense matter equation of state, such as how protons and neutrons arrange themselves and how many protons are present at a given density. Superfluidity modifies these processes, further suppressing or enhancing neutrino emission in different temperature ranges. The balance between modified and direct neutrino cooling, and between neutrino emission and heating from accretion and crustal reactions, determines how the internal temperature of the bursting pulsar evolves over long timescales. Observations of surface temperatures and luminosities, including during quiescent phases when accretion is low, provide indirect constraints on this balance, but the information is not yet precise enough to select a single model of core composition and cooling. Deeper into the core, densities may reach several times the density inside atomic nuclei, and the nature of matter becomes even less certain. At these extremes, various theoretical possibilities have been proposed. Some models predict that strange baryons known as hyperons appear, adding new particle species to the mixture as it becomes energetically favourable to convert some nucleons into particles containing strange quarks. Others suggest that meson condensates or other collective states could form. At still higher densities, some theories propose that nucleons may dissolve into their constituent quarks, producing a phase of deconfined quark matter that could behave as a colour superconductor, with quarks pairing in ways analogous to the pairing of electrons in ordinary superconductors. These possibilities are supported by calculations that extrapolate known nuclear physics into regimes that cannot yet be reached experimentally, but they remain uncertain because of the difficulty of solving the equations of quantum chromodynamics at high density, and because of the lack of direct observational signatures that uniquely identify any one exotic phase. What is better constrained observationally is the overall relationship between the mass and radius of neutron stars, which depends on how compressible dense matter is. Measurements of neutron star masses from binary orbits combined with inferences of radii from X-ray spectra and pulse profiles place limits on the acceptable equations of state. Some models that allow very soft matter, which would produce small radii for typical masses, are disfavored, while others that require matter to be very stiff, producing unusually large radii, are also constrained. Within these bounds, a range of equations of state remains viable. Bursting pulsars contribute to this effort because their bursts and persistent emission provide opportunities to measure surface gravity, redshift and radius through detailed modelling of their spectra and pulse profiles, though uncertainties in atmosphere composition, magnetic field geometry and distance still leave room for multiple solutions. The deepest core, where densities are highest, hides behind all these layers and cannot be observed directly. Instead, its properties are inferred from how the star as a whole behaves. If the core contains components that allow very rapid cooling by neutrinos, a young neutron star would cool more quickly and appear dimmer at a given age than it would if cooling were slower. If the core is very stiff, the maximum mass the star can support before collapsing to a black hole is higher. If it is softer, this maximum mass is lower. The existence of neutron stars with masses around twice the mass of the Sun already rules out some soft equations of state. For a bursting pulsar whose mass is measured with sufficient precision, such constraints narrow the range of allowed internal compositions. However, in most systems, including many bursting pulsars, the mass and radius are not known, with the accuracy needed to distinguish finely between models. Within the core, matter responds to the stresses of rotation and magnetic fields in a way that is both collective and constrained by fundamental physics. The fluid can support differential rotation between its layers, though coupling through magnetic fields and superfluid vortices tends to reduce such differences over time. It can respond to changes in the accretion torque by adjusting its rotation gradually with superfluid and normal components, exchanging angular momentum. It can support global oscillation modes including pressure and gravity waves that may be excited by burst accretion events or crustal fractures. Some of these oscillations would emit gravitational waves, ripples in space-time that carry energy away, but the predicted amplitudes are small and have not yet been detected from individual neutron stars. The presence of such modes, their frequencies, and their damping rates depend on the equation of state and internal composition. In principle, precise measurements of oscillations in electromagnetic or gravitational signals could reveal details of the core, but in practice, such observations are challenging and remain a goal for future instruments. In the context of the bursting pulsar, the deep core provides the central mass and gravity that shape every aspect of the system. Its equation of state determines how large the star is for a given mass, which in turn sets the surface gravity, the redshift of radiation, and the location of the inner accretion regions. Its thermal properties and neutrino emissions set how heat from accretion and crustal reactions is absorbed or carried away, influencing the long-term temperature of the surface and accreted layer. Its superfluid and superconducting components influence how quickly the star can adjust its spin in response to accretion torques and how internal stresses build and relax. At the same time, many details of the core remain beyond current empirical reach, and multiple internal configurations are consistent with existing data. In this innermost region, the bursting pulsar thus serves both as an astrophysical object and as a natural laboratory for dense matter physics. Observations of its bursts, pulses, and long-term thermal evolution provide indirect clues about what lies beneath the crust, but they do not yet assemble into a single definitive picture. The core continues to support the overlying layers to supply the gravity that confines accreted matter and to respond to angular momentum and heat, flowing from outside even as the precise arrangement of particles and phases deep within it remains one of the most significant open questions in the study of neutron stars and dense matter.